In this episode, we focus on a problem that is easy to miss when you are new to security engineering, but it becomes one of the biggest causes of real-world failure as systems grow. Security intent gets lost as work moves from idea to design to build to operation. Teams start with good goals, but then requirements change, designs evolve, shortcuts appear under schedule pressure, and months later nobody can clearly explain why a control exists, what risk it was meant to reduce, or whether it still works. Traceability is the discipline that prevents that drift by keeping a clear line between what was required, what was designed, what was built, what was tested, and what is being monitored. Software Development Lifecycle, SDLC, gives you a flow of activities where traceability can be established and maintained, and Model-Based Systems Engineering, MBSE, gives you a way to represent system structure and behavior so that traceability is not just written in words, but anchored in models. The goal is to make these ideas feel practical for beginners by showing how they keep security decisions accountable, evidence-backed, and resilient to change. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A simple way to understand traceability is to imagine that every security requirement is a promise, and every promise needs a trail of proof that stays intact as the system evolves. If the promise is that only certain users can perform sensitive actions, you need to know where that rule was captured, how it shaped design, where it was implemented, and how you verified it. Without that trail, you end up with confidence that is based on memory and assumptions, which is fragile because people forget and systems change. Traceability also protects teams from unproductive debates, because instead of arguing about what someone intended, you can point to what was approved and what evidence supports it. Beginners sometimes think traceability is paperwork that exists for auditors, but in practice, it is a survival tool that prevents security from turning into folklore. When a system experiences an incident, traceability helps you answer the most important questions quickly. What should have happened? What actually happened? And what changed that allowed the gap? That speed matters because the longer uncertainty persists, the longer risk remains unmanaged. The SDLC matters here because it provides natural points where traceability can be created and refreshed rather than relying on one big effort at the end. Early in the lifecycle, traceability begins with requirements, because requirements define what must be true for the system to be acceptable, including security constraints and assurance expectations. In the design stage, traceability connects those requirements to architectural decisions, such as where trust boundaries exist, which components handle sensitive data, and where authorization is enforced. During implementation, traceability connects design intent to real behavior, which is where many systems quietly diverge if no one checks. During verification and validation, traceability connects test evidence to the specific requirements it supports, preventing the common problem of having lots of test results but no clear proof that the right things were tested. Finally, during operations, traceability connects monitoring and change control back to requirements so that confidence remains justified after deployment. When you treat the SDLC as a continuous traceability engine, you stop thinking of security as a phase and start thinking of it as a thread. MBSE strengthens traceability because it shifts system understanding from scattered descriptions into structured representations of how the system is put together and how it behaves. A model is not just a picture. It is a way to capture components, interfaces, data flows, states, and constraints in a form that can be reviewed, compared, and updated as the system changes. For beginners, it helps to think of a model as a shared map that teams use to avoid getting lost, especially when many people are building different parts. Security becomes traceable in a model when security requirements are linked to specific elements of the system, such as a boundary where untrusted inputs enter, a component that holds sensitive records, or a workflow that performs privileged actions. When those links exist, a design change is less likely to silently break security because the model reveals what the change touches and what requirements might be impacted. MBSE also supports clearer conversations because stakeholders can discuss security in relation to the system's structure rather than relying on vague statements. In exam-style reasoning, a model-driven mindset helps you spot where assumptions live and where evidence must be collected. A major beginner misunderstanding is believing that traceability is only about tracking documents, when it is really about tracking meaning through transformation. Requirements are transformed into design. Design is transformed into implementation, and implementation is transformed into operational reality, and each transformation is a chance to lose intent. Security is especially vulnerable because it often shows up as constraints and edge case behaviors, which are easier to overlook than primary features. Traceability protects meaning by forcing each transformation to be explicit, so you can see how a requirement is realized and whether the realization still matches the requirement after changes. This is why traceability is not optional in mature security engineering, because without it, the system becomes difficult to assure and difficult to change safely. When teams cannot trace security intent, they tend to overreact by adding controls blindly, which increases complexity and can reduce reliability. A traceable system can evolve more confidently because changes can be evaluated against known requirements and known design choices. That balance between change and confidence is a central theme in ISSEP thinking. Security requirements are the first anchor point, and keeping them traceable begins with how they are written and how they are owned. A good security requirement is clear about what must be true, not just what tools should be used, because tool-specific requirements can become obsolete while the underlying need remains. Requirements should also be specific enough that someone can determine whether the system meets them, even if the exact method of verification evolves over time. This is where beginners often struggle, because they either write requirements that are too vague to verify or too detailed too early to remain stable. Traceability improves when each requirement has a reason linked to risk, because that reason helps later teams understand why the requirement matters and prevents it from being removed casually during refactoring. In a model-based mindset, requirements can be linked to system functions and interfaces, which clarifies what parts of the system are responsible for satisfying them. When a requirement is traceable, it becomes a guiding constraint rather than an afterthought. Architecture and design are where traceability becomes visible in structure, because design choices determine where security controls can actually work. If a system design mixes trust levels without clear boundaries, then later teams cannot easily trace where validation and authorization should occur, and security becomes scattered. If a design defines clear interfaces, data flows, and responsibility boundaries, traceability becomes easier because each requirement can be mapped to a location where it is enforced and to evidence that it is working. This mapping is not just a diagram exercise. It helps prevent predictable failure modes like trusting unvalidated input or allowing a component to gain privileges that were never intended. MBSE helps by representing these boundaries and flows explicitly so that security reasoning is grounded in system structure. When you can point to a boundary and say this is where untrusted input enters, you can also point to the requirement that demands validation there and to the evidence that validation is happening. That linkage turns security from a hope into an engineered property. Implementation is the stage where traceability often breaks, not because teams are careless, but because the pressure to deliver features can crowd out the discipline of aligning behavior with intent. A requirement might demand that access decisions are enforced consistently, yet a developer might implement a shortcut that works for a feature demo while quietly bypassing an authorization check. If traceability is strong, such a deviation is more likely to be detected because the implementation can be reviewed against the mapped requirement and the design intent. Traceability also helps when multiple teams contribute code, because it provides a shared understanding of which component owns which security responsibilities. Without that shared understanding, teams may assume someone else is enforcing a control, leading to gaps that are hard to spot until an incident occurs. In a model-based approach, implementation can be compared to the model's intended interactions, revealing unexpected calls, data flows, or privilege paths. For exam purposes, it is important to remember that security failures often come from mismatches between intended design and actual implementation, and traceability is what makes those mismatches discoverable. Verification and validation are where traceability becomes evidence, and evidence is what transforms security from a claim into justified confidence. Verification checks that the system meets specified requirements, while validation checks that it meets real needs in its operational context, and both require traceability to be meaningful. If you have test results but cannot show which requirement each result supports, you may have activity without assurance. Traceability supports targeted testing because you can identify which requirements are most critical and which parts of the system enforce them, then gather evidence that those parts behave correctly. A model-based approach also supports more thoughtful verification because the model clarifies expected behaviors, interface contracts, and state transitions, which can be used to identify where security must hold under stress. Beginners sometimes assume that security testing is a separate set of tests, but traceability encourages security verification to be embedded in the same disciplined approach used for other quality attributes. When verification evidence is traceable, it remains useful after changes because you can see which evidence must be refreshed and which requirements might be impacted. That repeatable evidence cycle is what keeps security traceable over time. Change is where traceability proves its value, because change is inevitable and uncontrolled change is one of the fastest ways to lose security posture. When a system changes, the question is not only what changed, but which requirements and security assumptions are affected by the change. Traceability provides the answer by linking system elements to requirements. So a change to an interface can be traced to the security constraints that apply to that interface, such as validation, authentication, or logging. This prevents a common failure pattern where a small change is made for convenience, and the system slowly accumulates exceptions that nobody can fully explain. In an MBSE approach, the model is updated to reflect the change, and the links from requirements to model elements help reveal what needs review and what evidence must be updated. For beginners, it helps to see traceability as the safety rail that allows you to move fast without falling off a cliff, because it keeps changes connected to intent and accountability. Exam scenarios about configuration drift, repeated reintroduction of issues, or inconsistent environments often indicate traceability breakdown across changes. Strong answers often focus on restoring disciplined change evaluation through traceability rather than merely adding more controls. A major benefit of MBSE is that it helps you reason about interfaces, and interfaces are where security boundaries live and where predictable failures often occur. Systems rarely fail because a single component is weak in isolation. They fail because components interact in unexpected ways or because one component trusts another more than it should. A model that captures interactions makes it easier to identify where untrusted influence could cross into high-trust logic, where data moves into less controlled contexts, or where authority is concentrated in a fragile pathway. When security requirements are linked to those interactions, you can trace exactly why a boundary exists and what checks must happen there. This also improves communication because different teams can align on the same representation of the system rather than relying on different mental pictures. Beginners sometimes believe models are too abstract for practical security, but models become practical when they reveal what is otherwise hidden, such as implicit trust chains and unintended dependencies. For exam reasoning, being able to identify and reason about trust boundaries and interface contracts is often the difference between a shallow answer and a defensible engineering answer. MBSE supports that reasoning by turning system structure into something you can inspect and keep aligned. Traceability also supports governance and accountability, because security decisions are not only technical but also organizational. When a requirement is accepted, modified, or deferred, someone should be accountable for that decision, and traceability ensures the decision is connected to the requirement and to the system elements it affects. Without traceability, risk acceptance can become informal and invisible, which leads to the dangerous situation where nobody remembers what risks were accepted and under what conditions. A traceable approach makes exceptions explicit and bounded because you can link an exception to a specific requirement, a specific system boundary, and a specific mitigation plan or monitoring expectation. That linkage helps organizations manage risk responsibly while still delivering systems, because trade-offs become documented choices rather than accidental outcomes. MBSE can contribute here by providing a clear view of how a decision affects system behavior, which makes it easier for authorities to understand consequences and approve responsibly. Beginners sometimes feel that governance is separate from engineering, but traceability is the bridge that connects them because it turns technical requirements into accountable decisions with evidence. Exam scenarios that involve unclear approvals, conflicting expectations, or repeated unresolved issues often point to missing traceability in governance decisions. Operational monitoring keeps traceability alive after deployment, because a system that is not observed cannot sustain justified confidence. Many security requirements are not fully proven by pre-release testing alone, because operational reality includes real users, evolving threats, and unexpected conditions. Monitoring becomes part of traceability when the monitoring signals are tied to specific requirements, such as auditing privileged actions, detecting unusual access patterns, or confirming that critical controls remain enabled and effective. If monitoring is collected without a traceable purpose, it becomes noise, and teams cannot confidently say what it proves. If monitoring is designed around requirements, it becomes ongoing evidence that security properties remain true, and it provides early warning when drift occurs. In model-based thinking, monitoring can also be tied to modeled interactions, so that you observe the boundaries and flows that matter most rather than watching everything equally. Beginners sometimes think monitoring is only for incident response, but in security engineering it is also for assurance because it verifies that the system behaves as intended over time. Exam questions that describe uncertainty about security posture, missing logs, or slow incident investigation often reveal that traceability did not extend into operations. A traceable monitoring approach helps keep security intent connected to operational reality. One of the most practical outcomes of combining the SDLC with MBSE is that you get a consistent story of the system that can survive turnover, scale, and time. People leave projects, new teams take over, and systems are maintained for years longer than anyone expects. And without traceability, security knowledge becomes a rumor that fades. A traceable system preserves intent in a form that can be relearned, such as requirements linked to models, models linked to designs, designs linked to evidence, and evidence linked to monitoring. That continuity supports safer evolution because future changes can be evaluated against the same underlying security promises rather than starting from scratch each time. It also prevents the common pattern where security reviews become repeated discovery exercises because nobody can point to what was decided and why. Beginners often underestimate how quickly complexity grows, but complexity is exactly why structured traceability matters, because it keeps reasoning manageable. In exam contexts, questions often test whether you can choose approaches that reduce long-term risk and improve assurance sustainability, not just immediate fixes. SDLC discipline combined with model-based clarity is a strong answer pattern because it improves security outcomes while supporting predictable delivery. As we close, the core message is that traceability is the mechanism that keeps security engineering honest because it forces a continuous connection between requirements, design, implementation, verification evidence, and operational monitoring. The SDLC provides the flow where that connection can be created and refreshed at natural points, preventing security from becoming a late-stage patch. MBSE strengthens the connection by representing system structure and behavior explicitly, making boundaries, interfaces, and dependencies visible and therefore manageable. When requirements are written clearly, linked to modeled system elements, and supported with evidence that stays current through change, security becomes a property you can defend rather than a hope you repeat. This approach prevents predictable failure modes like drift, inconsistent enforcement, and forgotten risk acceptances because decisions remain connected to accountability and proof. For ISSEP-style thinking, the best sign that you understand this topic is that you can explain how a security requirement travels through the system lifecycle and how you would know it is still true after changes and operational pressure. If you can do that, you are using lifecycle discipline and model-based reasoning to keep security traceable, which is one of the most reliable paths to secure outcomes in complex systems.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.